So at this point, what we're going to do is that we're going to consider the case when n is equal to 2 and L is equal to 1. And then for this case, we know that the third quantum number n can take on three possible values. It can be equal to -1, it could be equal to 0, and it could also be equal to +1. And then that means there are three possible solutions to the time-independent Schrodinger equation that we could construct. We could construct xi 211 r theta phi. And then for this case, the solution will be equal to R21R, which is just this expression here, times the y11 spherical harmonic. And then we can also construct xi 210 r theta phi. So don't forget that this corresponds to n, this corresponds to L, and this corresponds to M. And then for this case, we can construct this function by considering R21 multiplied by y01 theta phi. And then the third case is when xi has the quantum numbers 2, 1, and -1 r theta phi. And then for this case, it's going to be equal to R21 r times y -1 1 theta phi. So we want to construct these three functions, and then you can see that for these three functions, they're all related to R21, which is this expression, which we already have, except for the normalization constant. So what we're going to do first is that we're going to find the normalization constant, and then we can attach the spherical harmonics, and then we will have obtained the three solutions to the time-independent Schrodinger equation that we're looking for. So first of all, I just want to make a quick mention on what these expressions should be. So you can look up one of the tables that Griffiths gives us on the spherical harmonics. You'll see that y plus minus 1 theta phi is equal to minus plus 3 over 8 pi square root, so to the power of 1/2. So if this is positive, then this is going to be negative. If this is negative, then this is going to be positive. And then we have this constant multiplied by sine theta e to the power of plus minus I phi. And then also for y01 theta phi, so this would be used for this particular solution over here. And then if you look up the table, you will see that this particular function is equal to this constant multiplied by cosine theta. So now you can see that all that remains for us to do is to find R21 by finding the normalization constant. Once we do that, we can attach the spherical harmonics to obtain our solutions. So now what we're going to do is that we're going to normalize this function. And so we're going to consider this integral. So if we integrate from 0 to infinity, r squared times r21 absolute value squared dr, then this is going to be equal to 1. And so what we're going to do is that we're going to take this expression and then just square it. So by squaring this, you can see that we have c0 squared, and then divided by 16 a to the power of 4, and then we are going to have a r squared multiplied by another r squared, so that's r to the power of 4, and then we're going to square this e term. So it becomes e to the power of negative r divided by a. So we get rid of the 2 in the denominator, and then dr. So we're going to pull a similar trick as we did last time. So first of all, what I'm going to do is that I'm going to let r over a be equal to u, so that means du is equal to dr over a, so that means dr is equal to a times du. So what I'm going to get is that the bounds stay the same, it goes from 0 to infinity. This r to the power of 4 becomes a u to the power of 4, and then we have e to the power of negative u, and then the dr becomes a du. So you can see that we can pull out the a to the power of 5 over to the outside. And so what we're going to get is that we have c0 squared divided by 16, and then we have an a, and then we have integral from 0 to infinity, and then we have u to the power of 4 times e to the power of negative u du. And then we're going to do the same thing as we did last time. You can see that this is actually the gamma function. And so we know that from the formula that a gamma function n is equal to n minus 1 factorial if n is an integer. And this is actually the expression for the gamma function when n is equal to 5. So this entire expression, this entire integral, is actually going to be equal to 4 factorial. So of course you can also use integration by parts to solve this explicitly, but it will be faster if I invoke the gamma function. So this integral is equal to 4 factorial, which is equal to 24. And then these two numbers have 8 as a common factor, so we get 3 and 2. So in the end, you can see that 1 is equal to 3 over 2a c naught squared. So c naught squared is equal to 2 divided by 3a, and so this implies that c naught is equal to the square root of 2 divided by 3a. And so this is the normalization constant. So going back here, you can see that we have essentially constructed our R21. So now we're ready to find these three expressions. So first of all, let us consider these two cases. So both of these cases are pretty similar to each other. The only difference is that for the quantum number m, this is positive 1 and this is negative 1. And I can actually express both of them using a single expression. So I'm going to write plus minus 1 r theta phi, and then this is going to be equal to r21r multiplied by y plus minus 1 divided plus minus 1 theta phi. And then r21, as we found, is equal to c naught, which is equal to the square root of 2 over 3a applied to the remaining terms. So 1 over 4a squared r e to the power of negative r divided by 2a, and then we multiply it by this y term over here, which, as we have copied down, is equal to this. So let's just copy it down one more time. 3 over 8 pi, and then we have sine theta e to the power of plus minus I phi. And you can see that some of these terms, you should be able to cancel some of these terms out. These 3's, they cancel out. This 2 cancels out. You get a 4, and then you have a square root, so it becomes a 2 on the outside. So the 2 combines with this, you get an 8. So what remains in the square root is a and a pi. So in the end, what we have is minus plus 1 over the square root of pi and a. So we've taken care of these. And then we have these other constants that are not inside a square root term, so 8a squared. And then we have these terms, r e to the power of negative r divided by 2a. So we've taken care of these, we've taken care of these. And then we have sine theta, and then we also have this e term. So there you have it. This is your solution. So this expression will give us these particular solutions to the time-independent Schrodinger equation. So now we have constructed these two. So now this is the only one that remains to be done. So we have xi 210 r theta phi, and then once again this is equal to r21 r multiplied by y01, which is this expression, so square root of 3 over 4 pi. So let's just copy down the r21 first. So once again we have square root of 2 over 3a divided by 1 over 4a squared, and then r e to the power of negative r divided by 2a, and then we have the y term, so the square root of 3 over 4 pi times cosine theta. So 3 over 4 pi divided by times cosine theta. So all that remains to be done is to simplify some of these terms. So we have a 2. So I'm just going to keep this 2 inside the square root. So for the square root terms, we have a 2, we have an a, and we have a pi. So we have 2 pi a. And then we have some other constants not inside the square root, 1 over 4a squared. And then we have these terms over here, this r and this other r term. And then we also have a cosine theta. And so there we have it. This is your xi 210.